Having defined what the greatest common factor of a set of numbers is, we're going to learn a nice way to compute it called the Euclidean algorithm. The Euclidean algorithm is going to be very important for us moving forward. So here's an example. Can we find the greatest common factor of 126 and 1960? Well, if we do a whole bunch of tedious computation, we can find that the positive factors of 126 are the following list. In theory, what you would do is you would just check using the algorithm we already have, is one number a factor of the other? Is 1 a factor? Is 2 a factor? Is 3 a factor? Is 4 a factor? Etc., etc., etc. Run that algorithm 126 times, and here are the numbers that are in fact factors of 126. It would be really annoying to try to do by hand the same thing for 1960. It's technically feasible. Here they are. Okay, so we have now a list of all the positive factors of 126 and a list of all the positive factors of 1960. And again, in theory, you could actually check one by one. I certainly didn't do it that way. There are other ways to get this list, but in theory, one could at this point just manually check all, 1960 possible factors. But now if I look at the two lists, the only common factors are 1, 2, 7, and 14. Those are the only numbers that appear in both lists, and therefore the biggest common factor is 14. Okay, this was not a fun or convenient way to do this problem. But there it is, we have an answer. There must be a better way, however. We're not going to just do this really awful manual computation every time we want to find the greatest common factor. So here is the Euclidean algorithm, presented as a theorem. Suppose b and c are natural numbers, so we're just getting rid of negative numbers. Remember that the greatest common factor will not care whether a number is replaced with its absolute value or not. So suppose we've done that and we're only looking at natural numbers. Furthermore, let's assume that b is less than or equal to c. Of the two numbers b and c, either b is less than or equal to c or the other way. Let's just assume that b is less than or equal to c. Also, we're going to assume that c is not 0. Note, if c were equal to 0 and b is a natural number less than or equal to 0, then they'd both be 0, and then the greatest common factor does not exist. So once I assume that b is less than or equal to c, and I want to compute a greatest common factor, I should assume that the larger number is not 0. Well, under these assumptions, if b is 0, then the greatest common factor of 0 and c is c itself. But if b isn't 0, then the greatest common factor of b and c is the same number as the greatest common factor between the remainder when c is divided by b and b. Okay, so this replaces one computation of a greatest common factor with a different one. We will see, however, once we prove that this is true, we will see why this is really convenient. Well, under the assumption that b is 0, okay, we want to address this first part of the theorem first, if b is 0, every integer is a factor of b. Every integer is a factor of 0. But since c isn't 0, the largest factor of c is c itself. We don't need to work with absolute values because we've already assumed we're working in the natural numbers. So every integer is a factor of b. The biggest factor of c is c itself, and therefore the largest common factor is c itself. So that's the first part of the claim here. It's pretty straightforward. The second part is the one that is more interesting. Let's assume then that b is also not 0. But the division algorithm now guarantees that there is one unique choice of q and r, where q is this quotient and r is that remainder, so that I can write the following. So let's suppose that c is equal to bq plus r. What we're going to do is show that the common factors of b and c, so the set of integers which are common factors of b and c, is the same set as the set of integers that are common factors of b and r. Suppose a is a common factor of both b and c. Well, we've already established that a must therefore be a factor of any linear combination of b and c, any bx plus cy, where x and y are integers. This was a theorem from a previous video. Specifically, we're going to multiply b by negative q, and we're going to multiply c by 1. So if a is a factor of b and c, then a is a factor of c times 1 plus b times minus q. In other words, it's a factor of c minus bq. But looking up here, c minus bq is just r. So if a is a factor of b and c, a must be a factor of r. So any factor, any common factor of B and C is also a common factor of B and R. Remember, we assumed it was a common factor of B and C, so we already know it's a factor of B. Once we get that it's a factor of R as well, it must be a common factor of B and R. So the common factors of B and C are a subset of the common factors of B and R. But if we go the other way, let's assume that A is a common factor of B and R. Well then, A is a factor of any combination of B and R, specifically R plus B times Q, but R plus B times Q is exactly C. So if A is a common factor of B and R, then A is also a common factor of B and C. So not only are the common factors of B and C a subset of the common factors of B and R, but the common factors of B and R are a subset of the common factors of B and C. In other words, the two sets are equal. So since the sets of common factors of BC and the common factors of BR are the same set, well then the largest number is the same between both of them because they're the same set. So the greatest common factor of B and C is the same as the greatest common factor of R and B. And that's exactly what was claimed up at the beginning. The greatest common factor of B and C is the same as the greatest common factor of R and B. So what? Now that we know that for any two positive numbers, the greatest common factor of B and C can instead be computed with this division algorithm application, we get a really, really nice recursive algorithm. So suppose you input two natural numbers where C is not 0. If B is 0, you output that the greatest common divisor is C. The greatest common factor of 0 and C, as long as C isn't 0, is C itself. If, however, B was not 0, instead compute this as your greatest common divisor and say that that will be the same answer and output that instead. So if B isn't 0, then I can apply the division algorithm, and this remainder term does exist, but more to the point, it's smaller than B. So I was interested in finding the greatest common factor of B and C. The assumption, remember, was that B was less than or equal to C. We didn't put it in here because it turns out to not be necessary, but that's kind of how you should be thinking about it, that B should be the smaller of the two numbers. Instead of computing B is small and C is big, greatest common divisor, now we're going to be computing a greatest common divisor where this is smaller and B is the larger one. So we have replaced our computation of a smaller number and a bigger number, find the GCD, with now that what was used to be smaller, B, is now the bigger number. And you have a different number as your smaller entry. And you can repeat this process over and over, continuing to reduce the size of the numbers in question, which makes the problem much easier very quickly. Okay. So as the program keeps calling for more and more GCDs, the first value is always smaller, and it keeps getting smaller. Okay. This number here, this remainder, is definitely smaller than B. If I have to do it again, what used to be B now is replaced with a remainder and gets even smaller. So that first value is going to keep getting smaller and smaller, meaning it's eventually going to hit 0. And once that smaller number is 0, this algorithm can output the obvious answer and then stop. Okay, so let's look at the same example we did before. Find the greatest common factor of 126 with 1960. So according to the Euclidean algorithm, because these are both non-zero numbers, I can, instead of computing the GCD of this medium-sized number and this large number, I can compute the GCD of this small number and this medium-sized number. Now we do have to run the division algorithm to compute this remainder. It's 70. So we started with a medium number and a big number, and now we have a somewhat smaller number and a medium-sized number. But I can do this again. 70 takes the second spot, and I take the remainder as the first spot. Okay, what position is where doesn't really matter. I just like to keep the smaller number in the first location. We run the division algorithm, except at this point, 126, the remainder when divided by 70, is kind of easy to just spot by hand. It's 56. But notice now that instead of 126, 1960, we had 70, 126, and now we have 56 and 70. The numbers keep getting smaller. Apply the division algorithm again, 14 and 56. Apply the division algorithm again. The remainder here, 56 over 14, the remainder is 0. But now that I have a GCD of 0 and something else, the answer is whatever that something else was. So by repetitively applying the division algorithm until we hit a 0, we're able to compute the GCD of two numbers. That's the Euclidean algorithm. So whenever you begin with two numbers that aren't both 0, you just keep applying the division algorithm and your remainder term is going to keep getting smaller and smaller. It actually gets smaller quite quickly. It's exponentially fast, if you want to be particular about the speed of this algorithm, until one of them is 0, and then you're done. Okay, so the division algorithm can't be applied once you have 0 in one of the spots, but we simply know that the GCD of 0 and another non-zero number is whatever that other number was. So let's take a look at another example. Compute the GCD of 414 and 28. Observe I've violated my own rule and I've put the larger number in the first spot. Well, let's not be clever and just mindlessly apply the Euclidean algorithm. So the first thing I do is I take this first number and I put it in the second spot, and I do second divided by first remainder and I put it in the first. But the remainder, when 28 is divided by 414, is just 28. So we ended up switching the positions so that the smaller number was first, but we didn't have to think of that as a separate step. Applying the Euclidean algorithm naively did that for us anyway. Well, now I do it again. First number goes in second spot. Remainder, when second is divided by first, goes in first. We do have to apply the division algorithm to compute that. It's 22. Apply it again. 22 gets shifted to the second spot. I compute this remainder. Now it's pretty obvious. It's 6. Apply it again. 6 goes in the second spot. Compute this remainder. Again, not too hard. It's 4. 4 goes in the second spot. That remainder is pretty easy to compute as 2. 2 goes in the second spot, and that remainder is pretty easy to compute as 0. But now that I have a 0, I know the GCD is whatever the other number was. It's 2. Okay, let's do another example. Compute the GCD of 281 and 50. Well, we're just going to do the same thing again. Okay, we're going to write fewer lines just to save ourselves some effort, but we're just executing the Euclidean algorithm. So here, in terms of notation, I've put 50 in the second spot, and I've computed the remainder of 281 over 50. It's 31. I'm just not writing quite as many lines just in order to save some space. Well, 31 takes over the second spot. Compute the remainder of 50 over 31. The remainder is 19. 19 takes the second spot. The remainder of 31 over 19 is 12. 12 takes the second spot. The remainder of 19 over 12 is 7. 7 takes the second spot. The remainder of 12 over 7 is 5. 5 takes the second spot. The remainder of 7 over 5 is 2. 2 takes the second spot. The remainder of 5 over 2 is 1. 1 takes the second spot, and the remainder of 2 over 1 is 0. Now that I have a 0 in one location, the GCD is whatever that other number was. And therefore, the two numbers are relatively prime. Remember, the definition of two numbers being relatively prime is that their greatest common divisor is equal to 1, and we just showed that that's the case for these two numbers. So 281 and 50 are relatively prime. Can the Euclidean algorithm somehow function to find the greatest common factor of more than two values? The definition of greatest common factor applies to sets of 3, 5, 7, whatever, different integers. So can the Euclidean algorithm, a nice, convenient, fast way to compute the greatest common divisor, be applied? Yes. Suppose I have a set, okay? Well, the greatest common factor exists if and only if they're not all 0. That's not something that's very hard to prove. It's not really very different than the case of two integers, okay? If two integers are both 0, then there is no greatest common factor. If they're all 0, there's still no greatest common factor. Consider it on your own time. Suppose that I have 3 or more numbers. One of the numbers is 0, but not everything is 0. So I've got at least 3 numbers in this list. The first one is 0, but not all of the rest of them are. Then the greatest common divisor of 0 and a bunch of other stuff is equal to the GCD of all of the other stuff with that 0 thrown out. In other words, if the greatest common factor of a set exists and one of the elements is 0, you can kind of ignore it. Okay, and again, we're going to omit the proof, but because every number is a factor of 0, The greatest common factor of the rest of the numbers is really what's controlling what's going on. Okay, next, suppose that k is at least as large as 2, and you have a list of all those natural numbers. Then the Euclidean algorithm gets adjusted as follows. Instead of looking at the greatest common factor of this list, shift everything over one spot. So B1 is now in the second spot, B2 is in the third, and so forth. And then take the remainder of the last one over the first one and put that in the first location. Here's how we're adapting the Euclidean algorithm. First over last remainder goes first, and everything else just shifts over one spot. And again, you would have to go through and prove this, but it's not all that different from the one that we've already been working with. So make the first element in the list the remainder of last over first, move everything else one over. So since that remainder is going to be smaller than B1, suppose you begin with the list going from smallest to largest. Then you get rid of the largest and you replace it with something even smaller than what used to be the smallest one. And then the idea sort of carries over quite nicely. And you keep applying this until you are done, because if at any point there's a 0 remainder, this theorem here tells you you can just get rid of it. You don't need to worry about the zeros. So whenever a 0 remainder pops up, okay, throw it out, and now you have a shorter list to work with, and then you just do it again and again and again until you're done. Okay, we're not going to present this as a flowchart. Technically, we haven't really addressed working with lists of unspecified length, and it would get a bit messy incorporating all these various checkpoints into it. It becomes difficult to fit on one slide, essentially. But the fundamental process is not all that different. So let's do an example of applying the Euclidean algorithm to a longer list of numbers. Specifically, compute the greatest common factor of 9, 12, 20, 31, and 50. Well, I've already put them in increasing order, so what we're going to do over and over again is take the largest, find the remainder when divided by the smallest, make that the new smallest number, discard the old big number, and whenever a 0 pops up, just throw that away. So we start the process by saying, take 50 over 9 and take that remainder, and otherwise just shift everything over in the list, and now you can get rid of 50. The remainder when 50 is divided by 9 is 5, so observe most of the numbers here are the same, but we've replaced 50 with the remainder, 50 over 9, and that remainder is 5. Do that again, 31 over 5 remainder, and otherwise shift everything over. Well, that remainder is 1. Do that again, 20 over 1 remainder, and otherwise shift everything over by 1. The remainder when dividing by 1 is always 0, and when a 0 pops up, get rid of it. And now try again. 12 over 1 and then 159. Well, that remainder is 0, so get rid of it. 159. 9 over 1 is 0 remainder, so get rid of it. 5 over 1 remainder is 0, and now I have a pair of numbers. The first one is 0, so the GCD is just 1. So it's really the same idea, it just takes a few more steps, but it's amazingly fast and really quite easy to apply. So the Euclidean algorithm is a wonderfully quick way to compute the greatest common factor of 2 or really any list of numbers. There is another approach to applying the Euclidean algorithm to longer and longer lists. The way we did it before was very iterative in its approach. Replace something with a remainder. If it's 0, get rid of it. Replace something with a remainder. If it's 0, get rid of it until you're done. This next approach is a bit more recursive in its approach. So suppose you have 3 or more integers. Well, we already know that any zeros in the list will not affect what the greatest common divisor is. So suppose that they're actually all positive. We've preemptively gotten rid of any zeros in our list. Then the greatest common divisor of this list here is equal to the greatest common divisor of this list. And it doesn't look like I did anything, but observe, in this list, B1 and B2 are 2 separate numbers, and they're in the set that I'm taking the greatest common factor of. Here, B1 and B2, I find their greatest common factor first. This parenthetical term is now one integer, whatever the greatest common factor of B1 and B2 is. Then I make that the first element of the list, and I leave everything else alone. So instead of 2 separate numbers in the list, this is now one number, the greatest common factor of whatever those first 2 were. And that's really what we're doing, okay? Any pair of numbers in the list, instead of having them as two separate numbers, compute their greatest common factor and make that now a single number in the list. And that immediately reduces the length of the list until you're down to two numbers and you can just apply the Euclidean algorithm. So we're not going to go through the proof of this. It's pretty straightforward, and I would suggest you attempt to do it on your own. But since we already do have one way of applying the Euclidean algorithm to longer lists, we're not going to take the time, especially since this video is already over 20 minutes long, to do a proof here. But as an example, let's try to apply it to the same list we had before. So first we apply the Euclidean algorithm to 9 and 12 and get that their GCD is 3. So in the original list, we replace 9 and 12 with 3. Now I have 4 numbers. If I apply the standard Euclidean algorithm, the GCD of 3 and 20 is just 1. So replace 3 and 20 with 1. The greatest common factor of 1 and 31 is 1. So replace that with just 1. And then the greatest common factor of 1 and 50 is 1 by the standard Euclidean algorithm. So overall, the answer is 1. This approach simply says, instead of worrying about computing greatest common factors of long lists, as long as you can compute the GCD of a pair, just do that over and over again. Okay, so it's just another approach, and if you prefer this, you're free to do it. We are really only going to be focusing on greatest common factors of pairs of numbers. Greatest common factors of longer lists is not going to be terribly important for us, but it is nice to know that we can handle it if it were to come up.